Bismillahirrahmanirrahim. Assalamualaikum and very good day to all of you. So let's proceed our lecture on the title of magnetostatic field. Right? If you can see from the words of magnetostatic, actually, as shown here, the magnetostatic, right? Okay, this metal words actually refers to the only magnetic field exists in this field. It means that there is no electric field. So this word of magneto shows us that only magnetic field exists, right? So here, the magnetic field only. And then for the words of static here, it shows us that the field here is actually time invariant field or time independent field, right? So it's time independent. Okay, as we recall last time when we learned about the E field, the E field actually refers to the electric field intensity. So the same thing goes here. We can have also the magnetic field intensity, and now we denote as H. The H here, guys, actually have X, Y, and Z parameters, and there's no time factor because it's time invariant field. So the H here, guys, we denote as, and the name of H actually magnetic field intensity. Magnetic field intensity, and the H field has unit of ampere per meter. And the second one, we have here also magnetic field density, and that one we denote as the B field. The B, and also have only S, Y, Z parameter, doesn't involve any time factor. And now the name of B actually the magnetic field density, which is Weber per meter squared or Tesla. You can put either one, units are same. Alright, so let's recall our last time when we learned about the E field. The E field, we know that the source of E field actually comes from the static charge. It means that the charge that doesn't move at all. But for this case, actually the source of H field or B field actually come the charge that actually move but with constant velocity. Why? You can see from these equations, the J is equal to the rho V U, and the J is current density, and now we show that the charge that move with constant velocity will have a current. So that's why we can say that the source of H and B field in this case actually come from the current that move with constant velocity, or we can name it as DC current. Alright, so let's discuss about types of source for the H field. So as we have for the last E field, we also have few sources. Same thing goes here. We can have multiple sources of H field. So the first one, let's say we name it as filamentary current. So the first one here, let's say this is your current flowing into any conductor. This current or conductor flowing the I through it, and let's say we are going to take a sample. So let's say that's your sample. So, and this sample or this current element have a changes of length as shown here, let's say a dl. Alright, so this sample of this current element, guys, actually we name it as filamentary current element, and has a formula of I dl, and for sure the unit become ampere times meter, so become ampere meter. So this IDL actually our filamentary current element for the first case of source of H field. And DL here, guys, could be in any form depending on system that given to you. For this case of Cartesian, the DL here you can just convert to become dx dx plus y dy plus d dz. And also for the case of cylindrical, you can have the dl as well, become r dr plus phi r dphi plus z dz. And also for the case of spherical, you can have the dl as well, become r dr plus theta r sine theta d theta plus phi directions r d phi. So depending on structure that you are dealing with, so just substitute the dl depending on the structure given to you. So let's look at the second type of source. Here you can have the name as surface current. So let's say we consider a portion of surface current. Let's say this form of surface current, and this surface currents having a surface current density as Js. Alright, this current or this surface current having a surface current density as Js, and the Js having unit of ampere per meter. Okay, Js is your surface current density. So if you're going to take a sample or the current element within this surface current, so let's say that's your current element, and this current element also will have a certain direction. Let's say as shown there, the Js. So we can have here this one becoming your surface current element. Okay, and this one we can put into this equation, become the Js ds. Alright, so that's your surface current element. So this is your Js, and then this is your ds involved, small changes of area. So in this case, this element we name it as surface current element. Same thing goes to the previous one. We have here the unit of ampere meter. Why? Because the Js here having unit of ampere per meter, and times with meter squared, you're gonna have ampere meter. So we can say that surface current element has same unit with filamentary current element, which is Am. Alright, okay, let's proceed to the third type of source of H field. So this case we can just consider the volume current. Alright, let's say you have this structure of volume current. Okay, so for this volume current, they have the volume J, the volume current density for the structure. Actually, the J here we name it as volume current density, is a J, right? And this volume current density has a unit of ampere over meter squared. Okay, so let's say I want to take a sample or current element within this small structure of volume current. So this current element actually can come from this, the J dV, and this current element for this case, same thing, will have unit of ampere per meter. Why? Because the J here has unit of ampere per meter squared times the meter cube. You're going to have finally become ampere meter. So this is called as volume current element. Okay, so these are the three types of current that we must know before we go proceed to find the H field and the other field. So something goes here, and here we name it as filamentary current element, and this one surface current element, and then the last one here is your volume current element. Alright, so let's recall our last equation of Coulomb's law, which we use that to find the E field. So the Coulomb's law, okay, the Coulomb's law here, before we have here dE is equal to the dq over 4 pi epsilon naught r squared with vector of r, isn't it? So the dq is your sample of charge. It could be either rho L dL, could be rho S ds, could be rho V dV. So these three are called as sample of charge depending on type of structure that you are dealing with. Okay, now the same thing goes to the new law that we're going to deal with now. Actually, the law here to find the dH, actually we name it as Biot-Savart's law. Alright, this is called a BSL. So if you see from the structure of Coulomb's law equation, you can see the same pattern but slightly different. So here we have sample of charge. Here also we have sample of current or current element. So let's say you choose the first one, become your I dl, is it? Your first current element, the simplest one. And then here we have R. Here also we have the AR here. The vector of R over, so 4 pi, and now don't have the epsilon because this one only valid for the E field, R squared. So look at carefully to these equations. You see that this one actually is a vector, and this is also vector, but now here is your vector as well. If you leave it like that, something wrong with this equation. So you must remember to adjust the equation to make it valid. So if you put a dot there, so the output must be scalar, but now not, it's a vector, right? So the best way is actually put a cross product over there, and now the equation valid because this vector cross vector you have a vector. So that's the equation for the Biot-Savart's law, and this one can be used to calculate the any H field or B field within any structure given to you. So let's proceed